Welcome to week 3 of Stat 400 in the University of Bridgeport. So this week, we will be looking at bivariate analysis and hypothesis testing. We will be looking at t-tests and correlations. We now know how to get information about a variable. But what happens when we see two means that are close but not equal? How do we say that one is truly different from the other? Think of this example. If one section of Stat 400 has an average score of 89 and the other an average score of 87, is the first section really better than the second? It's only a 2-point difference. So for this, we're going to run a t-test. So a t-test is used to determine if two sets of data are significantly different from each other. These two sets of data are basically talking about the same thing, as we said before, grades. One set is section 1, the other set is section 2. So again, we're going to be testing, are they different or are they the same? So to be able to create this test, we have to write down what these tests are. Again, are they the same or are they different? And in statistics, what we do when we're testing things, we call this hypothesis testing. So in a statistical hypothesis, we have what is called the null hypothesis, which is saying that things are equal. And we have the alternative hypothesis that things are not equal. In the alternative hypothesis, we can actually go a little bit more specific, not only asking are things different, but is one bigger than the other? So, how do I know whether to retain the null or the alternative hypothesis? Meaning I'm going to run a t-test or other tests. How do I know which one is the one I will be retaining? So, retain or rejecting the null hypothesis, and what does it mean? In a t-test, as in other statistical tests, we will get what is called a p-value. The p-value is telling us the probability that the difference is due to chance or luck. An example, if a baseball player hits a home run, how much was due to luck and how much was due to skill? Think about it. Similarly, if we observe a p-value of 5%, so you'll see a p-value coming out from the test of 0.05. And we would like to interpret it as follows. There is a probability of 5% that the difference between the two classes, think about the example of 89 versus 87, those two means, was due to chance. There's a 5% probability that it's just luck. Most likely, you will conclude that it wasn't simply luck and that one class's average grade was significantly higher than the other. So again, these tests produce p-values, but whether you're going to retain or reject the null hypothesis and accept the alternative hypothesis if you reject the null, it's a matter of saying, well, what percent, what is the threshold, what is the bar I'm going to use? And some of that is theoretical. Some of that is, again, you'll just have to use your better judgment. So, following the theme of grades, do you believe the more you study, the better the grade? It depends. Run a correlation between grades and hours studied. So in other words, again, back to the question, do you believe the more you study, the better the grade? You'd want to know that because, again, as you have children and you're telling them, study more, and they're saying, I don't need to study. Well, if you're going to tell them, say, no, you need to study more so you can get better grades, well, why don't you prove it? So again, for this, we will use correlations. What is a correlation between grades and hours studied? That would be an interesting test to do. So let's talk more about correlations. So a correlation in statistics is a measure of how one variable changes with respect to the change in value of another. What is meant by this is that if variable A increases by 1, what happens to variable 2? Does it increase by 1? That would be a 100% correlation. Or does it decrease by 1? That would be a negative correlation of 1.0. Or does it go up by 0.2? Does it go down by 0.17? Again, there are many forms of correlations, and they're not always linear. However, in this class, we will be testing linear correlations. Again, increase in one, what happens to the next? So linear correlations can be positive or negative. We understand the degree to which two variables are correlated by taking note of the correlation coefficient. We'll be looking at that in the next video when we see examples of correlations running in R. However, take note here we have a strong positive correlation. Again, as one increases, so does the other, and so forth. Here we have a strong negative correlation. As this one increases, as this increases, this one decreases, and vice versa. Here we have kind of a weak correlation, positive, a weak correlation, a moderate negative. But again, so you're seeing that there's kind of like a general direction, but things are kind of scattered. Here we have a general direction going down, a little scattered, not too scattered. Here, I would agree, you can't determine a correlation here. Think dots are all over the place. So, strong warning, a significant correlation does not infer causality. Meaning that just because two things are related to each other doesn't mean that one causes the other. Maybe it does, maybe it doesn't. Later in this class, not in today's class, but in the following weeks, we will look at causality. Again, an example is that age and income, they may be correlated. You see that people, as they progress in their career, usually tend to be making more money. But it doesn't mean that older people should be paid more simply because they're older. Okay, so now let's do this in R.